We'll discuss about the introduction of plastic and what is the advantages of plastic over metals and a few categories of plastic parts in automotives. Some commonly used materials which we are using with their short forms, their applications also. And what are the basic considerations while designing a plastic part? And little bit about the plastic injection molding machine and molds also, and various stages of development in automotive component, and some injection molding defects in last. So let us start with the introduction. So the plastics are basically the polymers. So we can consider this as a chain of a small unit. When they are hooked together, so they becomes a chain of polymer, which is also called plastics. So at present time, everybody is using plastic in different areas, directly or indirectly. Everybody is using plastic. So plastic has replaced the metals in different areas, in different applications, because of some advantage. So these are the advantages which, because of that, the plastic has been replaced the metals. Like they have higher tensile strengths over the metals. Part weight is reduced as compared to metal, and manufacturing cost is also reduced. And we have more design flexibility with plastics. We can make more critical features, more critical geometries with the plastic. Waste is also reduced. If we compare, for example, if we are making the same part in sheet metal, so there will be more wastage when we will make a layout of some component on a strip. So wastage will be more in that case. And packaging and shipping cost is also less because weight is also less, and life is also long. We have longer life in plastic, and plastics are corrosion resistance. There is no problem of corrosion in plastic parts, and the plastic part can be available in any color, and highly aesthetic surface can be achieved in that. If you have seen the interior parts of automotives, like instrument panels and door trims, all those have a different type of surface finish, like graining. Some are like leather finish, some is pointed finish. Many kind of finish we can see there, and there is no secondary processes required like painting. In case of metal parts, we can have the original color in plastic part. So these are the common advantages of plastic parts, due to which we are replacing metals by plastic. So if we divide the parts in automotive, so there are like 4 categories. First one is the interior parts, like all the door trims, console, and instrument panel. And external parts like the bumpers, mudguards, spoilers, and back door garnish. Those are the exterior parts. And some are the engine compartment parts, like air supply systems, HVAC, engine lid, oil ducts. And some are bodyworks, like fuel tanks. So in these 4 categories, we can divide the automotive parts. These are the commonly used injection molded plastic parts. We can see here there are many varieties, many grades available in the market as per their properties, their composition, their make. So infinite number of grades are available, but these are the basic materials which are used commonly. Like first one is PP, polypropylene, which is mostly used for the bigger parts. It is also one of the cheapest part in available plastics, injection molded plastics. So this is used for like bumpers, door trims, some kind of instrument panels also, all the big parts which we can see in our automotive. So generally these plastics are not the bare materials. We add some fillers in that to improve the properties of those plastics. Like we can see here, the PP glass filled 30%. GF30 means glass filled 30%. So the glass is the filler in this basic material of PP. Sometimes we use mineral also as a filler to improve the properties of the basic material. So when we add the glass in the PP, this improves the stiffness of the material. It makes the material unscratchable. Those kind of things we can have. So now ABS is used. See, ABS and ASA, these two materials are used in the same application. The only difference is ABS is used for the painted parts and ASA is used for the non-painted parts, which is exposed to direct sunlight. Because sunlight deteriorates the surface finish because of ultraviolet rays. So if we are not painting the part, then we will use the ASA. Like all the ORVM, outside rear view mirrors in the vehicle, the covers of that part is made of ASA. If it is painted part, then it will be made in ABS. Like PA6 and PA66. These are the two most commonly used variants of polyamide, normally known as nylon also. So these are used for the structural parts, like frame or inside part, which is actually making some structures, some brackets, kind of things. PBT is a very hard material and it's very critical for processing also. So this is also used for the where high hardness of material is required. So in that case, we use PBT. POM is basically used where it is expected, where motions or some movement is required in the part, like hinge or something, where lubrication is expected from the material. And PC is polycarbonate. PC, PMMA, these both materials are mainly used for transparent plastics. But PMMA is more expensive material, have better quality than PC. So PC is used for like headlamps and tail lamps. And PMMA is a chemically inert material. So this have more advantage on PC, but at the same time it is expensive than PC. So PEHD and PELD. PEHD is polyethylene, high density and low density. So this material is used if we talk about the automotive, like all the spoilers, all the mud guards, all the parts which is not important in terms of aesthetic. So PE is used. And PCABS and PCPBT is again the composition of material. In PCABS, the ABS will be the main material. PEC is just added in small quantity to improve the properties. And same here in PCPBT, the PC will be the main material and PBT will be added in small amount. So these are the basic materials which are used normally. So the plastic design consideration. So these are the common consideration which when we are starting any design of any plastic parts. So these are the points which we need to consider. So first one is the tooling axis or draw axis. Like in our for injection molding plastic, in injection molding, so there are two things. One is the cavity and second one is core. So this is cavity is always fixed normally. and core is moving half. And this yellow one you can see this is a part. So if we see here that the cavity will be fixed always, and while injecting, after injecting the plastic material here, this moving half will move in this way. So whatever the direction we will use for opening the core and cavity, that is called the tooling axis or draw axis. So when we are starting any part designing, so first of all, we need to decide that what will be the tooling axis for that part. Then after that, we need to design all the features, all the clips, mountings, bosses, everything on that. So second one is the parting line. So parting line, what is parting line actually? When the core and cavity both meet together. So after that, we will inject the material into that. So when the both half meets, so at that meeting point, there will be a small gap. So metal will try to escape from that gap, and after solidification, you will see the surrounding line around the part. So that surrounding line is called parting line. It is not possible to avoid that parting line. That will be always there because in between two steel halves, we are trying to seal the molten plastic material. So there will be always chances to have small line. But yes, if the mold design is of good quality or mold manufacturing is good quality, so we can minimize that visibility of that parting line. But it is not possible to avoid that completely. Third one is draft angle. So draft angle, you can see if like see, this is in now this mold is in closed condition. So what will happen after the injection? We will inject the plastic material in the cavity. Then after that, this will open. Actually, this will remain at this location. This will not move. This core half together with part will move. So just imagine if this line, if this part don't have this angle, if this will be straight, so when this will come out from the cavity, this will always rub against this surface if this would be the straight. So we have always angle which is called draft angle, so that when this will come out from the cavity, after a small movement of part, this will be released from the all around surface of cavity, and same for core also. So this helps to avoid any scratches on the A surface part. I think everybody knows about the A surface and B surface. A surface is the visible surface, which is for any part which will be visible to us. And B surface, and more important, we expect a more good surface finish on the A surface. And B surface is the opposite surface, which will be hidden by A surface and not so important. All the construction ribs and all the screws, everything will be there on that side only. So this helps to release the component from the core and cavity easily. So this draft angle is always required. And the normal value for this draft angle, if you can see that this is the draft tooling axis. So this angle will be called draft angle. And normally this is required minimum 0.5 degree. Now comes to undercut. So what is undercut? Actually, you can see the small projections here in the core and this small projection hole in part. So what will happen, like just try to imagine that this is in closed condition. So what will happen when this will try to open, come out from, or we can see that when part will try to come out from the core. So this projection will becomes an interference, becomes an obstruction for the part to get it release. So these kind of any projection which is uh, at different angle from the tooling axis is called undercut.
Amit ji,
Like
please try to finish in 2 minutes. Please try to finish in 2 minutes.
2 minutes.
Anji.
Okay. So now the sink mark is also one problem. We need to consider this also. Gate location is another things, and warpage also, and shrinkage also. Warpage is the problem we can see in some parts. The main wall of that is deformed. So this is also, we have many means to avoid that by adding some ribs there. And yeah, shrinkage is we know that plastic materials have tendency that after solidification of the plastic materials, they shrink for some amount. This is always considered in terms of percentage. Like if we want any dimension in solidified part 100 mm, then we need to make it bigger in our mold. So it will be like 1%, like 101 mm we need to make in mold. That will come after solidification 100 mm. This is a image of a plastic injection molding machine. So mold will be mounted here. So the molten material is, the granular material is poured from here, and this we have some heaters. Because of heat, the molten material is pushed by the barrel, by the screw. So we have tons of pressure. This is injected into the mold. After some time, we have some holding time to cool down to solidify the plastic material. After that, this mold will open here and part will come out. This is example of molding machine. This is one example of mold. This is called moving half, fix half. Fix half generally produce the A surface, and the moving half produce the B surface. These are development stages of automotive plastic component. So during development of one plastic part, these are the stages. First of all, the OEM will generate the A surface, whether this is aesthetic or non-aesthetic part. So we are using here the A surface generation for aesthetic part. So packaging surface generation. Packaging means that after generation of A surface, they will check that component surface can be put inside the vehicle. So that is called the checking of packaging. The third one is the feasibility check of A surface. So this A surface will be sent to the tooling guys. So they will check that this is toolable or not. After that pass, this will come for part design. So that will come for the tier 1 suppliers normally. So the B surface and all other features are added to that A surface. And then it comes for tooling feasibility check. Again, this complete part design with the A surface and B surface features, everything. So this complete CAD design comes for tooling feasibility check. Then it comes for the DFME and PFME. It is design failure mode and effect analysis and process failure mode and effect analysis. So this is also kind of check, feasibility check. So now this comes for the part design modification based on these two things, tooling feasibility and DFME, PFME. Then finally this part design after the modification is released for development, which includes the part CAD, GD&T, graining and test requirements. So this is finally checked for tooling feasibility. So then it goes for the mold flow analysis. Mold flow analysis is a software which predict any problems before making any mold. So it predicts that there should not be any issue, where we need to provide the gates and everything. So after that, the mold design and checking fixture design is the stage. Then it comes for the manufacturing of mold and checking fixtures. Checking fixtures is the you can say the general construction, which replicate the same environment for the part as this will be fitted in vehicle. Then after the completion of this manufacturing, this will comes for mold trials. So trials will done on the mold. We will get the actual parts. Then this part is get validated on checking fixtures, and finally on vehicles also for small quantity like 10 number of vehicles. When the customer OEM is satisfied with the quality of that part, they provide mold graining approval, means the leather graining or whatever the surface finish we required on the A surface. We get that approval and we start etching of mold. And part validation is again done on the CF, checking fixtures, and on vehicle also. At this time, this will be for bigger quantity, like 300 or 500 also. Then it's a PPAP, it will goes for PPAP submission. And finally, the mass production will start. There are some defects. If we have time, I can explain.
I think it is 20 minutes. We can stop here. Is there any question from participant side?
One question, Amit, I'd like to ask. We have shown undercut.
Yes, sir.
If there is a projection needed in the part, so how do you solve that undercut while you are parting the mold, or are you bringing the mold out or the part out?
Yeah, actually, sir, in that case, we have specific terms like sliders and lifters.
Thank you.
Sliders and lifters are used for actuating that directions, in the undercut direction.
Thank you. I just wanted that answer. That's it.
Like if this is the undercut, and in that case, we will make a construction here. And this small amount, which is making interference with part, this will goes in this direction first.
So you'll make the side course.
Yeah, side course.
Right.
Side core is general term, big term, but specific word is lifters and sliders. If it is like this way, if it is on the external side, this will call slider. And if this is constructed in this way, here internal side of part, it is called lifters.
Thank you.
Welcome, sir.
Very nice presentation, Amit ji. And thank you ji. And we will be, I am recording the presentation, and we will be uploading this on the YouTube, and we will share the link. If anybody is having some problem in this, there will be some issues, so he can intimate us. We will not keep the recording for that purpose. अगर किसी को इसमें थोड़ा इशू है तो बता दीजिएगा पहले रिकॉर्डिंग का. ये हम नॉलेज शेयरिंग के लिए कर रहे हैं. लास्ट टाइम कालरा जी का लेक्चर हुआ था और कालरा जी भी यहाँ पर हैं. तो विद इन 1 वीक देयर आर 100 व्यूअर्स फॉर द लेक्चर ऑफ कालरा जी. जो कालरा जी लास्ट लेक्चर, हाँ जी, दैट इज फैंटास्टिक. तो एक हफ्ते में 100 मतलब व्यूअर्स मिले हैं. और जितने हमने लेक्चर्स अपलोड किए हैं उनमें सबसे ज्यादा व्यूअर्स कालरा जी के लेक्चर के हैं.
तो कालरा जी के लिए तो बनता है 1 2 3 भाई वाह.
वाह भाई वाह.
सर अभी 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 थोड़ा सा 2-4 और इम्प्रूव्ड होगी, मेरी प्रेजेंटेशन ज्यादा वो नहीं थी, बट फिर भी मैं थोड़ा और डिटेल्ड में भी जाना चाहता हूँ। अगर टाइम मिलेगा तो थोड़ा मेरे को भी दीजिएगा।
नहीं बिल्कुल
2-3
सर,
प्रेजेंटेशन और भी है।
बिल्कुल सर।
यस सर।
Okay.
So
यस सर, थैंक्स अ लॉट।
thank you. Now I invite Anil Kumar Kaul ji for the presentation.
Let me share. How do I get into sharing mode? How do I share now?
I think सर नीचे एक शेयर स्क्रीन होगा ग्रीन, हाँ हो गया, आपका दिखाई दे रहा है शेयर।
हाँ अभी आ गया कॉल था।
Yeah. Okay. Okay, I'll quickly start because my presentation is quite long, and I would like you, this is more from the standpoint of learning which I'm sharing. This is about a problem solving approach we had done through Six Sigma, wherein you attain two methodologies. One is to improve the process rejection, and another thing is that how do you do the systematic and analytical way of problem solving. This was a case on uh, basically on RFT Improvement Project as a Six Sigma green belt project, which was taken by one of my boys, and I was the sponsor for that. And the project was improvement of right first time in conrod crimping of the Buran-10 compressor. We will go to the next slide, and quickly we see what the area of improvement was the right first time, which was in the crimping process of conrod crimping, which was at 52%. And we had taken voice of customer, which was the subsequent operations, high level CTQ. CTQ is critical to quality, which was the understanding the customer needs. And this is the data what we have on the right side of the slide. Quickly going on to the next slide, wherein we have really defined the project CTQ. CTQs, as I said, was critical to quality. What was happening was that we had seen in the Buran compressor, which is the pneumatic compressors used in railway coaches and in metros, wherein we had seen we had done 1,304 sides of conrod crimpings for 163 compressors, out of which 629 sides failed, and in that 527 side failures were due to excess depth or it was due to the load issue. On the right side, if you see, we took this 1304 crimpings what we had done. 675 of them passed and 629 of them failed. If you do look at the percentage wise, 52% passed, 48% failed, and that's how we drilled down that 40% out of this 48% was due to the depth issue, and due to the load issue there were 8%, which is 102. And then you go down and look into that what was the batch. If batch was 2018, which was 10%, and 2019, which was 30%, and then you further drill down into which was A side of the conrod, B side of the conrod, and similarly for the batches of 2019. And what were the parameters which were involved? Machine setting, process variation, material hardness, crimping, tool dimensions, etc. So what we adopted was in this methodology was to take in DMAIC approach, which was define, measure, analyze, improve, and control methodology. And we are into, if you will see on the right side, we are into the define. You will see on the top right hand side corner of the slides, we are in the define mode. So this was taken as a business case for the team to be taking up. The problem was clearly defined, the issue was the process depth and the load which was not meeting the specifications. The goal was to improve the right first time, and we prepared the project milestones, which was define, measure, analyze, improve, and control along with these dates. In between, the pandemic also came, so we had to slow it down. And we go to the next step, which was the team charter. So we prepared the team, and these were the members of the team, and we also analyzed that what was the role of each member of the team in this. So my role was, for example, to approve the specific team decisions. There was somebody to do provide the resourcing. Somebody had to act as a member in the team, and there were interested parties who would be kept informed upon. The next slide which we mapped was what was the process map. And this is starting from here. You can see the conrod heating and pressing. Then you got end crimping. Then you do the conrod crimping. You go ahead with a small end insert, and then you do the bearing insertion, and so on. And then you further go on the crankshaft and assembly and all that. I'll not go through all that because it's not relevant to the project. But you can see the red lines over here. These red lines show what is within the scope of this project. So we have mapped that part of it. Going to the next slide, where we in this we see the CTQ's characteristics. What are the customer needs? No failure in conrod crimping process. The business KPIs, the KPI measure, we want the 100% KPI target. What is the primary CTQ, which is the load and the depth, load in decanewtons and depth in millimeters, then the defects, the units, the number of units of conrod, and since it is going to be on both sides, so number of opportunities occurring in this part of conrod. We go to the next slide. Here we have said as business why, what is the why of this equation, which is the performance standards. Then we also bifurcate between what is discrete. For example, the pass means okay and fail means not okay. So that is discrete. And then you have continuous, which is load. This is the data type what we are going to have measuring the data on this. This is continuous data where you will measure and find the measurable values on this. And the defect would be, if it is, for example, for the load, if it is less than 4330 decanewtons and greater than 6131 decanewtons, because this was the specifications. And similarly for depth, if it was less than 0.3 millimeters and greater than 0.49 millimeters. So primarily then the project why was another important parameter was data collection. We go to the next slide. What was the measurement system analysis? We looked at the current measurement system, wherein the current crimping was done through a semi-automatic machine with the help of calibrated linear variable differential transformer and the load cell. And that is what we had taken it up. And there was no manual control in this. So the team decided that there is no R&R study required in this because this is already calibrated. You can see the machine, you can see the calibration report, you can see the load cell and LVDT. Then we took what is the current situation of the process. Current situation for process on the process capability side for the load was that we were getting Z value of 1.18 and DPMO was more than 1 lakh units. And this was the out of specification parts were around 11.88%. You can see the CPK values or PPK values on the right side of this, which we took it through the mini tab. And you can see the process overall process capability, what you can see it in terms of stats, what are there available in terms of figures. So this was for load, and we are into analyze phase in this. Then we go to the in terms of depth. Depth, you see we were getting a Z value of 0.26. DPMO was around 3,97,000. And the out of specification parts were 39.75%. Again, this was taken from the current process, what had happened, and plotted it through the mini tab, and we were able to see the PPK values, which you will see are pretty poor in this over here on the right side. I'll not spell them because it's too long a presentation. So going to what was the next step was to understand that what is the total DPMO what we get from both the processes, And what was our target? Our target was to reach to less than 48,000 from over around 5 lakh DPMO, which was the contribution both in terms of load and depth. Then we see what were the sources of variation. If you see, when we set up the crimping process, the load, these were the parameters which were involved, which was machine setting, waiting time, wall thickness, and power pack oil level. And in machine setting, there were 3 parameters, which was pressure, approach, power stroke. Similarly, for depth, these were the parameters, and these were the parameters again, pressure, approach, and power stroke for machine setting. So in this, what was done was, when we went to Gamba, and in the Gamba, in the Gamba, what was happening was we were able to see the process waiting time between conrod assembly and conrod crimping, wall thickness of conrod, press machine oil level, and crimping dimensions. These were all within the specifications. So we sort of eliminated these. You can see on the left side, since these were in the specifications, we thought because of since they were within the specifications, we had to eliminate them. Then we were able to concentrate on machine setting parameters only. And further we went, and then what we did was, we based on the vital X, and we thought it would be appropriate for us to do a design of experiments on these machine settings, wherein the factors were pressure, approach time, and power stroke. And there were 3 levels in each parameters, between 3, 4, and 5. This was time. This was the pressure levels, and in case of approach time, it was seconds. Power stroke time, it was seconds. So once you do the design of experiment, 3 factors, 3 levels, 3 to the power 3, and 4 replicates, it came to the number of trials what we had to do for in order to understand the DOE, what it is giving us. So we had to do 108 trials. So we did these trials both for load and depth. In this, you can see in this slide the physical layout of the trials. What we did was, this was 1 trial, and then we had to replicate 4 trials for each of these parameters for each of these levels. Having gone through that, then we did was, if you see over here, we came into the improve phase, and wherein we did ANOVA, analysis of variance, and where we saw that where is the effect of analysis of variance, wherein what is the p-value. P-value, if you will see that if it becomes significant, if it is less than 0.05, if it is more than 0.05, then it is non-significant. So having understood this, where through the ANOVA, we were able to see the pressure in the main effects was due to the pressure only, which was coming as statistically significant. And in the 2-way interaction effect, pressure versus approach, which you can see it over here, this was also coming as significant. And 3-way interactions, it was not coming as statistically significant. And this was for ANOVA, which we did for load. And you can see the interaction effect on here, the pressure, approach, and power stroke. These are the 3 parameters. And this is the interaction effect, what you can see on the right side. This is all done through Minitab. The conclusion was very simple. The important thing was the pressure was important, and pressure versus approach time was important, and this is what was correlated as positive. Then we go into the ANOVA on depth. Similarly, we did for depth, and we saw there were 3 important parameters which were having significance because of the less than 0.05 p-value, and where here we could conclude that pressure, approach time, and power stroke are statistically significant, you can see, because of the p-values over here. And similarly, in 2-way interaction, we saw that pressure and approach, this is also significant, and the 3-way interaction was also showing statistically significance over here. So having understood this, we went to see the interaction effect and the mains effect and the interaction effect in the next slide on through the Minitab, and wherein we were able to see that pressure versus approach time was positive, correlated to the load, besides the 3 main effects. Now, having understood that, again in this, we saw in the DOE, the machine setting, which was the machine setting which was giving us the optimal results. We came into that trial number 14 was giving us the most optimal results, and wherein then what we did was we took the number of crimpings on this settings, which was the trial number 14. We took 224 crimpings out of that. Number of pass were 190 and number of fail were 34. So the first time through improved to 84.8%. So finally, the conclusion of this was that trial number 14 is an optimal solution. Setting at these would result in 100% FTT. After we conducted the confirmation of DOE, the recommendation was that FTT reached was 85%, and this was 33% increase from the previous failures what we had. So the screen potential causes, if you see in this case, is that Z value is at 4.39 and DPMO is come to 6, and there was zero parts out of specification. We go further into, and this was for depth and load. The Z value was 0.79 and the DPMO was 2,15,000. Still 15% parts were out of specification. So what did we do further? We still wanted to achieve our goal at 100%. So what we did was we understood that the DOE machine setting conclusion is very clear. So we need to do further improvement on the process where we had reached to 85%, but 15% we still needed to analyze. So we went further into analysis and got into material thickness and material hardness, which were playing an important role further. Because if you see over here, the process capability of depth after DOE, still we had this 15% parts out of the specifications. Then we went into this. If you want look at this over here on this solution tree where the crimping failure was happening. So material hardness, which was 94 to 110 BHN, and material thickness, which was 21 plus 0.01, was also an important factor. So the conclusion was that we need to get into material thickness and material hardness. So here what we did was that we went into these two parameters. So initially we took the thickness part of it and we plotted again, and we wanted to use the regression model in over here. And we did a trial on 8 conrods on 16 sites and plotted them over here and understood what is the depth and load relationship in this. Here in the next slide, you would see that we were able to see that p-value is not coming less than 0.05, and this should be 0.05, hence it was not statistically significant in terms of material thickness. So we went ahead and saw the material hardness part of it. We adopted the regression model for this, plotted them over here in terms of BHN, saw the depth in millimeters, what is coming against the load. We took again the same 8 conrods and did 16 sides, understood what is the hardness value of A and B, then again plotted them in the Minitab, and we were able to see that they were negatively correlated with the depth. So which means if you see it over here, the higher material hardness was bringing in the depth within the specification limit if you are moving from 100 above 100 to 108 BHN, and the specification limit was 0.3 to 0.49. So as we go higher in the hardness, then the depth was getting controlled between 0.3 to 0.49. So this was the negative correlation we saw between the hardness and the depth. Thus, again, we did this experiment particularly for the conrods, wherein we had seen it is above 100 to 103, and therein we were able to see that we had conducted 33 crimpings on them, and more than which had the Pringle hardness number more than 98, and we were able to use the regression model to plot it. And we were able to see the improvement in this, which will be in the next slide over here. So what we were able to see that when we confirmed this trial of 33 slides, we were able to see when we do the machine setting of pressure 4 bar, approach time 3 seconds, power stroke 2 seconds, material hardness more than 98 bhn, we did 33 crimpings, all 33 passed, there was no failure, and FTT reached to 100%. So that's how we solved the problem, and we were able to do the improve phase. Then we were able to also put the relationship into that, and what relationship through the regression model came out, that this was the equation which came out finally for the depth and for hardness, which was X was the hardness. So you can see at different depths, what you will see at different hardnesses, this is the depth obtained for the crimping to happen. So at 104 it is 0.39, at 100 it is 0.42, and 108 is 0.37. So you could see a negative correlation happening over there through the regression model. Then going further, this was the final setting what we got for machine setting and for material hardness, which we were able to lay down the process control parameters through which we would be able to control the crimping process in order to bring down the rejection to 0. Then we also tried to understand what is the measurement system. If you see through the measurement systems what we had adopted, the repeatability was around 7.17 and gauge R&R was 9.53, which was less than 10%. And hence we did not need to do anything different in terms of gauge R&R, and this was we concluded that this is acceptable since this was less than 10% in variation. And it also passed the normality test, and you can see the normality over here for load, and the Z value was greater than 10, DPMO was 0. You can see the process capability over here. PP went to 10.16, and PPK was also 9.02. And as I said, for depth also similarly we passed the normality test, and the Z value was 2.39, DPMO 14.1498, and 0 parts were out of specifications in this. Then in order to implement further process control, what we told our supplier quality assessment team was that what they
Kaul
need to do,
can we stop here because it is 10 minutes over, I think.
We can stop.
थोड़ा सा जल्दी conclude कर दीजिए.
So this is the last, in fact.
Okay, sir.
We went to the supplier and saw how many parts were lying with them, and we could take a call on that how do we lay the specifications at the supplier end for hardness. So that's it. And of course you have to revise the various documentation of PFMEA and control plans for mistake proofing, etc. So that concludes the presentation.
Very nice presentation. Now session is open for the question answer.
And this was the savings what we got from it. Any questions are welcome.
कौल साहब, मेरा इसमें एक क्वेश्चन है कि आपने जो पार्ट बी दिखाया था उसमें कुछ वर्क असाइन किया था अपनी टीम को, तो ये कैसे किया जाता है? मतलब कि जैसे आप कुछ वर्क असाइन करते हैं तो कितने पर्सन हमें टीम में लेने हैं और कैसे कैसे उनको काम असाइन किया जाएगा, ये चीज कैसे डिसाइड की जाती है?
This is basically decided on see, there's two, three things. One is that who's the project sponsor. Like I was being a senior person, I was the sponsor, being a director of operations. Then you base it based on what are you getting as voice of customer. For example, हमारे को कुछ failures आ रहे थे on compressors from customer. So this was voice of customer. So important thing is we have to hear customer. So customer से आके, so that means field services का एक आदमी होएगा. Then we go into the manufacturing process. So process engineering से एक आदमी आएगा. Then quality, because that's involved, and as you have interface between the customer and the plant manufacturing process, so that part that person gets involved, and you basically take the team which is in line with the part going towards the customer, and कौन कौन उसमें इफेक्ट होता है. तो उन फंक्शंस में से एक एक रिप्रेजेंटेटिव लेते हुए आप टीम बनाते हैं, and then you also understand that what are the criticalities involved in this, and do you require any process expert or something. So that's how you select the team for any project. And what are the financial advantages? It's a business को advantage क्या हो रहा है, so that you see it financially. So do you require any commercial guy in this, in the sense that finance guy, to understand that what are the financial implications of this. So that's how you select the team.
Okay, thank you, sir. Very nice presentation.
Thank you, dear.
Now I invite Rajesh Chowdhry ji for the seminar.
Can you see the slides now?
Yes, sir.
Yes, you can see
And
the
I hope
slide.
I'm audible.
Yes,
audible.
Rajesh.
Okay. Respected professors and my fellow YMCA alumni, a very good evening to all of you. I am Rajesh Chowdhry, a pass out of 1987 batch. I have over 3 decades of experience in different roles with managing premium brands with the PLN responsibility, and the area of operation I have handled is India, SAARC countries and West Africa. I have been exposed to large organizations like Larsen and Toubro, Timken, Cummins and Schaeffler, which is FAG bearings. And I have also worked for some Indian family driven businesses like Lloyd Insulations and Gross Engineering Tools. My latest role is Chief Business Officer with Mosil Lubricants Private Limited, Bombay. We are talking about bearing fundamentals today. So this is a very, very interesting topic and close to my heart, because bearing industry is the one where I spent about 17 years of my career, more than 50% of my career. And my gut feel is that wherever I have gone, whichever customers I have met or whichever industry I have visited, I found that the knowledge of bearing is very, very limited. In fact, there are hardly any textbook, at least from the time we studied in the college, which talks in details about bearings. However, it is a very, very important part of the power transmission chain. And I think learning this is very, very useful and important for us. So our objectives in this presentation are review the need for anti-friction bearings, discuss the types, and focus on the design, function and advantages of different bearing types. What is the need of a bearing? As the name suggests, bearing means it should be able to bear the load. So if a load is coming on the housing, through the bearing it has to go to the shaft, or it is coming to the shaft, then through the bearing it has to go to the housing. So that is the most important function, and that is why it is called a bearing. The second function is the locating, because if it is a rotating part, if you don't locate it, then it will simply roll away. So you have to hold it in position or facilitate rotation. And finally, the third part is reduce friction. But the first two are more important than reducing the friction, because there are friction bearings also. And as we can broadly classify, the bearings can be plain bearings or friction bearings and the anti-friction bearing. So plain bearing, there are many examples like crankshaft bearings or bushes, which are used in many applications. There, the basic role is converting the friction to rolling friction, rather than the normal friction between metal to metal. It becomes a rolling friction. But anti-friction bearings, there is basically no relative motion. So here we will only discuss about the types of anti-friction bearings. So why anti-friction bearings? Because friction must be creating some problems. So first and foremost, the friction causes very high torque required for movement. Obviously, when you have a high torque, it will create a lot of heat and ultimately result in wear and tear of the parts which are moving against each other. So when we design an anti-friction bearing, the criteria would be in terms of performance with regard to size and geometry. That means what are the what kind of size we can build, how big should be dimension, diameter versus length, how much is the space available, let's say in a gearbox. The second part is what kind of load and speed capability we are looking at. There are bearings available which work on a speed as low as about 10 rpm or 5 rpm, and there are bearings available which are going into lakhs of rpm. If you know the drill which is used in the dental application, that means when you go to a dentist and he does a drilling in our teeth, that is running at about 3 lakh rpm. So there are bearings available which are facilitating that kind of speed also. The third criteria is life and reliability. So depending on how long is the service interval of the machine, how long you expect, like when you design a bearing for a vehicle, typically you are looking a life for about 5 years. If you are looking for a machine which is earth moving machine, you might be servicing it every year or something, so you are looking at 1 year life. So depending on the application, what kind of life you require. And finally, last but not the least, is what kind of cost you can afford to buy that bearing or put in that bearing. So any designer, when he is selecting a bearing, he is looking at basically these 4 criteria. Let's go to the nomenclature of the bearing. A typical bearing would have a outer race, a inner race. Can you see the pointer?
Very much, Rajesh. Go ahead.
I'm using the pointer for the first time in presentation, so I'm just making sure. It would have a rolling element which may look like a ball or a roller. And finally, there can be a cage. Cage is optional because there are many bearings which are cageless. There are basically or broadly 5 types of anti-friction bearings: ball bearings, spherical roller bearings, cylindrical roller bearings, needle roller bearings, and tapered roller bearing. So we will look at each one of them in little bit of detail. First of all, let's look at bearing loads. So there can be a radial load on the bearing which is acting perpendicular to the shaft, and most bearings can carry radial load. There could also be a load which can act parallel to the shaft, which could be axial load. So this, we also say that it occurs parallel to the direction of rotation, and shape of the rolling element basically would determine how well the bearing will handle axial load. As an example, if we use a ball bearing which will have balls as rolling element, it will be mostly able to use only a radial kind of load. Whereas a taper roller bearing or a spherical roller bearing, because of the shape of the ball, it will be able to handle the axial loads also. So let's look at each of the types now. Ball bearing, it is the simplest and most common type of anti-friction bearing. We see it everywhere, wherever we use electric motors. We use ceiling fans every day. We use a lot of other small equipment. Even in our house, we might use a mixer grinder, we might use a washing machine. So each one of them would be typically using a ball bearing. It will have a same outer race, inner race, and rolling elements will be basically looking like a ball. Ball bearing is very easy to assemble, and it is a low cost relatively. It maintains a single point of contact, and it has very high speed capability. A few minutes ago, I gave the example of the dentist drill running at 3 lakh rpm. That is again a precision ball bearing, because ball bearing is the only one which can take that kind of speed because of low friction due to the point contact. The ball bearings would not be tolerant of very heavy shock and axial load. So in heavy machines, typically we cannot use ball bearing, but in light duty applications, you will see it everywhere. So typical applications of ball bearing are electric motors, conveyor rolls, light duty gearboxes, and small vehicles. When we say small vehicles, if you see any vehicle coming from Maruti stable, typically the wheel bearings would always be angular contact ball bearings because the load is low and speed required could be medium to high over there. Let's go to the next type, which is spherical roller bearing. Each features two rows of spherical rollers. So that is why many places people call it DSR also, which is double spherical roller bearing. The curve of the roller matches the race, and if you look at the rollers, they look like a spherical in shape. So spherical but cut at the ends. So if you complete this part, which is cut at the end, then it will become a sphere. So because of the shape, as you can think of, the inner race and a spherical roller sitting on that, it should be able to take a radial load as well as a axial load. The most important property I should mention here is self-aligning. So in many type of manufacturing, typically if you look at castings, there are a lot of errors. You cannot make a very accurate casting, and that is why when you cast the housings, you will have some misalignment between the shaft and the housing. And spherical roller bearing can tolerate misalignment up to 0.05 radians. However, because of taking misalignment, it will always have a low rigidity and high shaft deflection. So think of an application where you require high rigidity or shaft deflection or very high stiffness in the shaft, like machine tool. So in no way you can think of using a spherical roller bearing in those applications. But you think of the other extreme, other end of the spectrum, where you require low to medium speed in gearboxes, in heavy gearboxes, where you require to transmit high power in cement plants, in steel rolling mills, etc. You can easily make spherical roller bearing at very low cost. The other thing is you also require a higher torque to run the spherical roller bearing. So that would mean that the friction will be little bit higher than the ball bearing. I already mentioned that gearboxes with fabricated housings in industries like cement, fertilizer, power, paper, etc. is the typical application for spherical roller bearings. The next type is cylindrical roller bearing. As the name suggests, the balls or the rollers would look like a cylinder. Very interesting thing here is everything is straight or at right angle. So that means it is a very simple design which will allow very tight manufacturing tolerances. It will have a line contact, which would mean it will enable very high radial loads. It will take very small amount of axial load. Again, it has a high speed and torque required to run the bearing. Because of straight and right angle, it will be very low. Typical application of spherical roller bearings are precision rolling mills and big electric motors, or what we call as HT motors. You will find cylindrical roller bearings being used on those applications. Needle roller bearing, practically it looked like a cylindrical roller, but if you see D by L ratio, that is diameter by L ratio, will be more than sometimes even more than 5 over here. So why do we need like that? The diameter is very small and length is very long, because in many places there is a very small space available in a gearbox in terms of diameter, but actually you can go as long as possible. So that is why in cylindrical roller bearing, they converted into a needle roller bearing kind of design. It can tolerate very light axial load and suitable for duties involving partial or slow speeds. Because of longer needle, it cannot take very high speed applications. It will have a thin cross section. It can accept very large shaft relatively for the size or design. It will again give very good stiffness and rigidity to the whole system. These are light duty bearings, and because of the long length of the roller, cage are typically guiding the roller. So there can be some friction between the roller and the cages. Typical applications are gearbox and reduction unit, where radially you have a space constraint, as I mentioned before. The last type we come to now is taper roller bearing. This is a very interesting bearing which combines many features of the other bearing. It has tapered rollers which are held in alignment by a cage, as you can see here, tapered roller. So to accommodate taper roller, you need a inner race and outer race which has a tapered surface. It has a true rolling motion. It's like if you take a cone and put it on a flat surface and push it, it will rotate and come back on the same place. So on the raceway as well as every point on the roller body, there will be a true rolling motion and no sliding. It has capability to carry any combination and of radial and axial loads. So this is how the assembled bearing looks like. You look at the cross section, so you have the roller and outer race and inner race. And obviously, relatively, you can move the outer race with respect to the inner race. It is a line contact bearing, which would mean it can take high load, only being able to handle radial as well as axial load and operate at slow to high speeds. It has adjustable settings. So if you look at, you can set up the radial clearance axially. If you see the picture on left hand side and then again see it on the right hand side and the exploded view, you can see that to increase the clearance, if you see in this picture, the outer race, if we move to the right hand side, then this clearance will increase, which would in turn mean that the radial clearance will also increase. So as an example, if we want to use it on a machine tool application, we would create a tight clearance by moving this outer race to the left hand side. And if we have a application very high load to be transmitted, but at a slow speed, then we will move the outer race slightly to the right hand side, so that there is maybe slightly less rigidity is where we compromise, but it will facilitate a higher speed and higher load possibility. Typical applications are medium to large vehicles. So this picture of the car is it's actually like an SUV. So bigger car on the wheel bearing, they would use typically a taper roller kind of bearing, or even trucks or mining equipment. Similarly, power systems, gearboxes where we have helical gears, spiral bevel or herringbone kind of gears. In all those combinations, you require axial load also to be managed, and there would be taper roller bearings used in application. Similarly, you have machine tool and printing presses where you need very, very high stiffness. Again, you will find many applications where taper roller bearings could be used. I think I have finished in about 15 minutes. I am open to any questions now.
Rajesh, one question I wanted to ask, I mean, this is just for my inquisitiveness, that how do you make the life of a ball bearing different? For example, if I need a ball bearing of life 1 lakh cycles, then how do you design it? And if I need it a 1 million cycles, how do you design it? So what is different in both?
Typically, you look at the size of the rollers, dia of the rollers and length of the rollers. In case of ball bearing, length of the roller will not be applicable. So basically dia of the roller and number of rollers basically will decide the bearing capacity. So suppose you are using a shaft of 50 millimeter diameter, you might have to increase the OD so that you can accommodate larger roller and higher number of rollers. And that is how you will increase the capacity.
Okay.
But if you go for a taper roller or cylindrical roller bearing or even needle roller bearing, you might increase it by increasing the diameter, you might increase it by number of rollers, or you might increase it by increasing the length of the rollers.
Okay, understood. So these are the parameters what you consider while designing.
Absolutely. So you basically start backwards. Exactly the way you are asking, that designer decides what kind of life is required for that application based on the overhauling cycle.
Right.
So
Okay.
then you work backward and then decide on, what is there an existing bearing available which fits in the given envelope, or you need to design a new bearing. There are so many, there are a few lakhs of bearing sizes available now. So the possibility of designing a new bearing these days is very, very rare.
Okay.
Most of the time you select from a catalog and then you calculate the life, and then if the, let's say, vehicle manufacturer and bearing designer, they are okay with it, they will go for prototyping, and then they will go for the initial testing, etc. right away.
Yeah, for the normal designer, it will be best for them to pick it up from the catalog and then design their product based on the available bearings in the marketplace. Correct?
That's right. It's always makes sense because bearing is a volume game.
Yeah.
So if there is an existing part number or existing bearing available versus you design a new bearing, the cost can be
Cost will be.
significantly different. You can, the two bearings may look of the same size, but one may cost 500 rupees and the other may cost 5,000 rupees, depending on the volume.
Okay. Thank you.
Any other question?
Rajesh,
Yeah.
Rajesh Upinder here.
Yeah.
So since you have spent a long time in bearing industry, can you please help general user understand how fitment of a bearing affect the life of a bearing? Because I know I've understood. So that fitting a bearing in a shaft in a thing is important.
Okay. Can you see? I'm trying to put a graph.
Some light on. Sure.
So basically, on one axis, I would put life. I'm using a mouse, so I'm not sure if I am to write properly. And on the other,
Being wonderful.
and on the other axis, I am trying to put the the fit. It could be in microns or whatever unit you want to use. So typically, as you increase the tightness, initially the life will increase and it will peak at a particular point. But after that, there will be a catastrophic drop in life. Like somewhere here is the zero. So this is a zero fit. And if you move further right, then it becomes a interference.
Okay.
INT. And on the left hand side, it is a basically in some amount of clearance. CL, I would write clearance. So from clearance, as you move to the interference, typically the life will fall catastrophically. So just to give you an example, a machine tool bearing, typically you may put slightly on this side, on zero side or slightly on the
right side.
Right side.
Correct.
But machine tool, the size of the bearing is so large that typically you are getting an infinite life when you do a life calculation. So even in that condition, in a tight fit, when you run, the life will come maybe 50 years. So you will hardly see a machine tool bearing failing. Similarly, ceiling fan bearing or a electric motor bearing also, when it is a ball bearing, it will fit on this side. But when you have a spherical roller bearing, then you may fit somewhere here. Because there the load is very high. So slightly also, if it comes on a preloaded state, there will be a catastrophic drop in life. So this is a very, very interesting subject, again close to my heart, and I can go on forever on
But
this.
won't it be dependent on that? I mean, there are two parts to it. One is the outer race this thing fitment and inner race fitment to the shaft.
Yeah.
So is it applicable for both for outer race and inner race for the shaft?
See, bearings are available in different clearance. If you ask about ball bearings or some types of bearings, So you can, C1, C2, C3, those terms you would have heard. So you can get in tight clearance, you can get in loose clearance depending on the application, and again it is specified by the designer. But if you go to the taper roller bearing, typically you can change the clearance based on the axial movement of the races.
Yeah, here it is clear.
Yeah. So, you can, there are ways of, you can put a washer here. You can, how much nut you are tightening here.
Preloading, you're talking about preloading.
You preloading or, end play, what we call. By tightening this bolt, you can do it here. But the ball bearings would be typically preset. So by fitment, you cannot change the clearance of a ball bearing.
Right. Okay.
But you can change a little bit by this fit on the shaft and housing.
Correct.
Here again, as Kulsab, you were mentioning earlier, a designer will go that in running condition, what condition he wants. Okay. And then he will work backwards that what fitment will be here, what will be the fitment between, outer race and inner race and shaft, and how much will be the loss of clearance because of running and heating. Because whenever you are running, housing is a bigger section. So there will be more heat dissipation. So typically there will be a 10 to 15 degree temperature variance between shaft and housing in running condition, and that will also cause loss of clearance.
Right, agreed.
So designer calculates everything backwards, and then he defines how much clearance you need at the time of fitment.
So you mean to say that the thermal compensation also is considered by the designer, correct?
Absolutely.
Because that plays an important role in terms of life of the bearing again.
Absolutely, especially applications where you are talking of tight fits like machine tool or gearboxes.
Right.
Gearboxes.
Okay, thank you.
Yeah, thanks, Rajesh. Very well explained. So I just wanted to raise this point because this is something which is not known to many people, and in the process they lose a lot of money in replacing the bearing before the exhaust reach.
Absolutely. Thank you so much. I appreciate the opportunity.
Hello, Rajesh ji. Hello.
Dr. Nikhil, can you be a bit louder?
Actually, someone else is asking some question, I think.
Rajesh ji.
Vinod Kumar ji asking something. Vinod Kumar ji, please
sir,
be.
How much play or backlash?
No, I can't hear. Can somebody repeat the question if someone else has heard?
Sir, how much backlash or play is allowed in bearings?
How much?
Backlash is Rajesh is asking for how much backlash is allowed in the bearings.
You will not have a bearing backlash. You will have a system backlash, and typically backlash you will find in gears, not in bearings.
Vinod ji, you can write your question in chat box if you are not audible. Rajesh ji, I am having 3 questions. That may be somewhat high, more number of questions. But my first question is, does the bearing require lubrication? And my second question is, as the area of contact in the bearing is very less, so the balls of the bearing should be very hard. So generally, what is the material which is being used for the ball bearing? And my third question is regarding the maintenance. As the balls of the bearing are being covered inside some enclosure, and if they are being cracked or there is some flaw, then we cannot identify by just looking them. So how it is being completed in terms of maintenance?
Okay, I'll go one by one. I think your first question is about the lubrication. Does it require lubrication? The answer is yes, because if we run without lubrication, it will immediately be a catastrophe. It will fail almost in no time, maybe in a few minutes itself. There will be a metal to metal friction and very high amount of heating and burning over there. So there will be a seizure. So the lubrication again depends on the application, which is, the load parameters, speed parameters. On high load, there are extreme pressure kind of lubricants which are available. There are normal, industrial oils and greases which are available. Again, type of lubrication can be grease lubrication, oil lubrication. Again, it is the ease of application. So it is recommended by the designer of the bearing. So then your second question was on material. The bearings typically are a very hard material between 58 to 64 Rockwell C. But we also require high ductility, high ductile strength and high tensile strength. So we use bearing steels, which are typically low carbon steels, and they are hardened. Most of the companies use a hardening process of the normal hardening, but the hardness is also achieved by induction hardening, case carburizing kind of processes. So, but on the surface you achieve a hardness of 58 to 64 Rockwell C and very high amount of finish. So the raceway and the rollers, not the OD. If you look at this cup, the outer race inner part and inner race outer part, and the rollers, they are finished through the honing process. So with a combination of very high surface finish, hardness and lubrication, you are able to achieve a high life. Your third question, have I answered the first two questions?
Yes, sir. Yeah.
The third question is about maintenance.
Hanji.
So yes, maintenance is very difficult. And in some cases, it depends a lot on the experience. But in many cases, bearings or the housings are designed in such a way that you are able to view the bearing, or you are able to open at a certain interval. Just to give you an idea, there are very large bearings, say about 1 meter or 2 meter diameter, and they are available in two halves. So you can easily install and remove because they are in two halves of 180-degree each. Nowadays, there are new technologies which are come up, which is called as condition monitoring. So they pick up the signal from the shaft and housing, and then those signals are recorded on a regular basis. So basically, if a bearing is rotating, there will be a different frequency coming for the roller and race, right?
Yeah.
Race may be 1 RPM and roller may be 20 times of that. So the signal will tell that where the frequency is changing. Similarly, it will also know that in the system, if there is a gearbox, how many gear teeth are there. So that vibration analysis or condition monitoring system will be able to tell us that which component has started wearing out. So based on that, when you are recording that reading on a regular frequency, let's say every week or every month, then over a period of time, you can decide and plan your shutdown for the plant to do the bearing maintenance. In fact, this technology started only about 20-30 years ago, and it has become so advanced now. They do vibration analysis, they do oil analysis, they do the balancing. And there is also a technology which is infrared thermography, which you monitor the temperature. So these 4 or 5 technologies together, they are used for doing the predictive maintenance for the bearing.
In railways, we use condition monitoring methodology to predict the life of the bearings for the wheels.
Absolutely. Condition monitoring could be even oil analysis, that you take out the used oil and you analyze it, and you will find the metal particles. So you can decide if they have come from the shaft or housing.
Correct.
Or
You understand the viscosity levels.
Ferroanalysis
Levels of the oil.
Yeah.
Ferroanalysis of the oil, spectrography of the oil, and all that. These are the techniques.
Absolutely.
Vinod has asked some questions.
In the chat box is there.
Chat box, Vinod has asked.
I am reading the question. The question is, how much play or backlash error is allowed for in bearing?
Okay, I think the play or backlash, what you are talking in bearing, we call it a clearance. So I think I mentioned this before, but I will repeat that in a typical high-speed application, you will require some play. But in a application where you have you require a lot of stiffness and rigidity like machine tool, there you actually are preloading. So it is a negative clearance. That means the surfaces are, pushing into each other. So it will again depend on the application, that what system stiffness, rigidity, what is the speed, what is the load coming, that designer will calculate the play in the system.
Rajesh ji, Praveen here. एक question है मेरा.
Yeah.
Okay, so one is that of course, it's a very large subject, bearing in itself, because there are some varieties of bearings, and today you covered up 3 specific one, which are mostly used in the industry. But my question may be a little bit out of that. Like, we are talking about nowadays frictionless bearing, like magnetic bearings or ceramic bearings. So magnetic is a totally different one, but ceramic bearings where the shafts are being in touch, and then they so is there some light you can throw on those bearings type versus these, because they are supposed to be using no lubricant, so it's in the sense no oil. It is, for example, it is used in the refrigeration industry now for large chillers, where refrigerant itself act as a lubricant for them. There is no oil or those kind of things.
So typically, if refrigerant has a lubricating property like a oil or grease, then that can be used. But there is
no, I think refrigerant only do basically the cooling, you can say, kind of ceramic bearing, take away the heat of the friction.
Typically, around the bearing where you have gauge, you would put a material which will be a matrix, and it will contain some kind of oil or lubricating material. So when the bearing is running, then matrix will release that lubricating material. So, but you can do that only on slow to medium speed application and low load application. Wherever you have heavy load, then you will require a external lubrication like grease or circulating oil or something of that sort. So in light duty application, you can use self lubricating bearing.
So I'm talking about large compressors, centrifugal compressors, where we are using this, which is typically, I'm saying in terms of, if I tell you capacity, it's close to 1,000 tons of refrigeration, in fact, compressor, using ceramic bearing without having any oil charge in the system.
I'll have to really look at the application. Basically, I am not exactly a ceramic application bearing expert, but definitely the basics will remain same. So if we talk about, in compressor, there can be several applications. So if it is a low speed, then still something like that might work.
Yeah, speed is in the range of roughly around 10,000 RPM.
Okay. 10,000 is a very high speed.
10,000 is high speed.
Very high speed, yeah.
Yeah.
I'll really have to look at, I
Okay.
can comment on that.
Sure. Thank you, sir.
My pleasure.
What is the range of diameter of the bearings in general? What is the smallest size and what is biggest size?
Smallest size, I told you, like the dentist drill. So it can sit on the tip of my finger. It can be so small. And biggest size of bearing can be, I have seen up to about 3 meter diameter. If you see the
probably in windmills. Oh, I see.
If you see the large windmills, typically it will use very, very big bearings, because the windmill blades are huge and you need a very, very big gearbox. So typically around 3 meter diameter.
I see. Thank you.
Yeah.
So very nice session.
Thank you.
Thank you, Ji. And is there any more questions? Otherwise, we can end here. Thank you for the today's presenter, Amit Ji, Anil Ji, and Rajesh Ji.
Nikhil Ji, Sandeep Gambhir this side.